Hey, what's up, class? How's everyone on this fine Friday? How was the exam, by the way? Not too bad. The usual. That's good to hear. So, what do you guys think of the exam? Every always feels like you don't have enough time. Yeah, yeah. That's how exams can be sometimes. What do y'all think of the exam every 2 weeks rather than two or three midterms and a final format? Like, do you prefer to have the more smaller, lower stakes exams? Or okay, I mean, I could see that. That's why we switched to that. Yeah, I can see that. It's also annoying to grade an exam every 2 weeks, but yeah, for sure. Yeah, it's kind of like there's never like any downtime. It's like, oh, it's that time again. Time to do all the reviews and get ready for the exam once again. But yeah, I could see it's a trade off. But yeah, oh, that's good. Every 3 weeks would be a bit better. Yeah, I guess that'd be wait, I don't even know how many. So yeah, it'd probably be like 4 exams, I'm guessing. Yeah, that'd probably be easier too. I guess it was easier just to chop up each exam in half. Maybe that's a little easier to do. But yeah, cool, cool, cool. Okay. Alrighty. So no, dude. Oh my god, I almost did it again. No, I almost stopped the recording. That's way too easy to do. Okay. Um, so today, so it says we're going to be looking at 12.7, which is just introducing um, polar, cylindrical, and spherical coordinates. I don't think we need to. I I'd rather not, spend a whole day just talking about those and not talking about the integrals. And I think it's easier to talk about, introduce polar coordinates and then do integration, and then introduce cylindrical and then do integration, and then introduce spherical and then do integration and spherical. Um, so I'm just gonna do, I think it's 15.3, 15.4, 15.4. And I'll just do a small amount of introduction that we'll need to do before we can get into integration. Anyways, okay. So we're gonna talk today about polar coordinates. So going back to double integrals today. Nice. Okay. So I believe y'all talked a bit about polar coordinates in 141, but we'll remind you a bit. about that, and then we'll look at integration using polar coordinates. So we've seen how to do double integrals over one type of more general region, and that is where either x or y is allowed to be bounded by functions. So either some region where you're either going to have a top curve and a bottom curve, or a left curve and a right curve. There are, of course, more general regions. There are regions which are neither horizontally nor vertically simple, and R2. Remember, we're doing double integrals, so now we're talking about regions in the plane. So the regions which are neither, but even then, there are some regions which are maybe one or both, but it's not well suited, the approach we were doing before to doing these types of integrals. They can come out rather nasty. But for example, consider something like this. And this is sort of a region tailor-made for using polar coordinates. So suppose D is the region in the upper half plane so where y is positive, which lies between x squared plus y squared equals 1 and x squared plus y squared equals 4. So you have the circle of radius 1 centered at the origin, the circle of radius 2 centered at the origin. You look at the region between the two, and you consider the region in the upper. You know what? Let's not even say in the upper half plane. Let's just say, yeah, we could do that. We could do that just to illustrate. So we have this little half annulus here. Consider this region D here. And suppose we want to integrate over that. Okay, so is this vertically simple, horizontally simple, both? Neither. Right? Let's look at vertically simple. If we do the vertical line test, is there a consistent top curve and a consistent bottom curve? So if you intersect a vertical line, is it always going to hit the same top and same bottom curve? No, it's going to have the same top curve, right? It's always going to be this upper guy, but depending on which vertical line you use, here, this is the bottom curve here in some spots. This is the bottom curve in some others, and this is the bottom curve elsewhere. So we would, in fact, if we wanted to integrate this, we would need to break it up into 3 pieces. Right? If you wanted to treat this as vertically simple, we'd have to integrate x from -2 to 1, and then we'd have x or y equals 0 be the bottom curve, and then y is equal to square root 4 minus x squared be the top curve, and then this piece here, the middle piece, where the bottom curve would be the piece of the circle of radius 1, the top would be the piece of the circle of radius 2, and then from x equals 1 to 2, where same thing, the bottom curve is y equals 0, and the top curve is the piece of the circle of radius 2. So probably rather not be doing 3 integrals on an exam. And then you run into a similar problem if you try to treat it as horizontally simple. But it's an extremely simple region if we use polar coordinates. In fact, as we'll see, it's basically a rectangle in polar coordinates. So it's what we call a polar rectangle. And it's very simple to deal with. So polar coordinates are basically regions which are pieces of circles. Yeah, so if you have regions bounded by circles, and you have just like sectors of those circles, that is basically where polar coordinates are tailor-made to handle that kind of stuff. But anyways, so let's remind ourselves, what are polar coordinates? Let's go to the next page. Let's give ourselves more room. So polar coordinates, we contrast these with rectangular coordinates. So whenever we're using x, y, z, the usual, so x, y in R2 and x, y, z in R3, we call those rectangular coordinates because, you know, you have a point x, y. Well, that is just x, the first coordinate is how far along the x-axis you go, and the second coordinate is how far along the y-axis you go, and they form this little rectangle here. Polar coordinates work a little differently. So with polar coordinates, we have a point, we use r and theta. So the r coordinate is going to be how far from the center, from the origin, are we located. So this is our point r theta. R is going to be distance from the origin. So you can think about it as lying on a circle centered at the origin of radius r. All those points are the same distance from the origin. And then the first coordinate r is just going to tell you how far from the origin you are. Theta is going to be the angle measured counterclockwise from the positive x-axis. So that is important that we're measuring it counterclockwise. We're measuring that big angle and not this little guy here. So for your point r theta, r is the distance of your point from the origin. Theta, so if you draw the line segment from the origin to your point, you're going to look at the angle that guy makes measured counterclockwise from the positive x-axis. Okay. Um, so usually, if we're just talking about a point, just to avoid a bit of confusion here, usually we consider R to be positive. But depending on the formula, we could have R being, we'll deal with that when we get to it. We'll deal with that. We'll just consider it like this for now. Let's just keep it like this. So R is your distance from the origin. Theta is the angle measured counterclockwise with a positive x-axis. So we have the following, very, very extremely important. Equations that you need to know. So here's how you convert from polar to rectangular, vice versa. X is going to be equal to R cos theta. And Y is R sine theta. Right, so why is that the case? Well, if you consider the circle centered at the origin of radius r, right? If you just consider the unit circle, x is the x coordinate is cos theta, and the y coordinate is sine theta. And then if you consider the circle of radius r, it's the same thing. X is going to be r times cos theta. Y is going to be r times sine theta. So you need to remember those, and then you could derive this from those, but I mean, this is something convenient to remember. X squared plus y squared is equal to r squared. So these you need to know immediately. Okay, any questions so far about polar coordinates? So, you know what, let's just jump right into integration. Why not? Okay, hang on, let's introduce polar rectangles. This is the whole reason why we're doing this, basically. Because very often we're going to want to integrate over regions which are bounded by sectors, pieces of circles. So what is a polar rectangle? So a polar rectangle is basically just like a rectangle. Remember, the rectangle that we talked about before is the set of points x, y, where both x and y, both variables, are bounded by numbers. Right? X goes from A to B, y goes from C to D. Polar rectangles are the same thing, but now both of our variables r and theta are going to be bounded by numbers. So it's a set of points r theta such that r is going to go from A to B, and theta is going to go from alpha to beta. And so here's what that's going to look like. Okay, so so if we consider the set of all points which are distance r away from the origin, right? That is a circle of, sorry, let's say distance a away from the origin. That is a circle of radius a centered at the origin, right? So the set of all points r theta whose r coordinate is equal to a. That's just a set of points which are distance a away from the origin. And so the circle of radius a centered at the origin, the equation of that guy in polar is just r equals a, right? It's a set of points r theta where the r coordinate is equal to a. Does everyone understand that bit? It's just a set of points distance a away from the origin. And then similarly, the circle of radius b centered at the origin, if we look at the set of all points which are distance b from the origin, that is just the circle, or the equation r equals b. The equation of that guy is r. So what are the points, if I just specify a theta, so if I say theta equals alpha, what is that going to look like? So suppose I have a single point where theta is equal to alpha, right? So it's r, whatever r is, alpha. If I look at all the points which have the same angle theta with the origin, made with the positive x-axis, those are going to lie along a radial line from the origin. Like, do you agree that all the points on that line have theta coordinate equal to alpha in this case? So suppose this guy here, this angle's alpha. All the points on that line make the same angle with the positive x-axis. So theta equals alpha describes this half line here. And then similarly, theta equals beta if this is beta here, that half line there is theta is equal to beta. Okay, so if we're looking at the set of all points which lie between distance a and b from the origin, so they lie between the circles r equals a and r equals b, and whose angle lies between alpha and beta with the positive x-axis, what we're looking at is we're looking at this region here. So that's our D. That's a polar rectangle. It's basically going to look like a piece of an annulus, a sector of an annulus. So all the points in there are between distance A and B from the origin, and the angle they make with the positive x-axis lies between alpha and beta. And that is what a typical polar rectangle looks like. So as an easy example, so let's describe the region D inside the circle x squared plus y squared equals 2. As a polar rectangle. In other words, say r goes from what to what, theta goes from what to what. Okay, so x squared plus y squared equals 2. Okay. So the circle x squared plus y squared equals 2, what's the radius of that circle? It's square root of 2, right? So the outer bit, the furthest away we get is that circle. And so that's the furthest away our points get. So r is less than or equal to square root of 2. What is the closest to the origin we get? What distance? 0, right? The origin's in there. So if the origin is in your set, r is bounded below by 0. That's something to remember. Okay, how about theta? So what's the smallest angle we make with the positive x-axis? 0, right? We have points on the positive x-axis, right? And then we go all the way around 2 pi. So theta goes from 0 to 2 pi. That's another good thing to remember. If you're going all the way around, you go from 0 to 2 pi. Sometimes it's more convenient to say from like negative pi to pi or whatever, but we'll say 0 to 2 pi. Okay, so these are the types of regions we're going to be dealing with. So integrating over a polar rectangle. So I'm going to use the same shorthand for polar rectangles that I do for rectangular coordinate rectangles. So if r goes from A to B and theta goes from alpha to beta. I'll call that A to B cross alpha to beta. And I'll just write in r and theta to emphasize that this is a polar rectangle, not a normal rectangle. We're not talking about x and y, we're talking about r and theta. So that's a region D. If we can describe some region as a polar rectangle, then if we want to integrate a function of x and y, so our function is going to be an x and y, over some region D, which we happen to be able to describe as a polar rectangle, what we have to do is we have to do a coordinate change. So if we want to integrate in polar coordinates, every time we see x and y, we don't want to see x and y, right? We want to change coordinates, so we're dealing with polar coordinates. So what we have to do is, remember, x is, like we said earlier, our cos theta. So every time we see x in our equation, in our function, we're going to replace with our cos theta. So this is in the function we're integrating. Every time we see y, we're going to replace with our sine theta. And r is going to go from A to B, and theta is going to go from alpha to beta. So dA normally becomes dx dy or dy dx. Here, it's not quite dr d theta, it's r times dr d theta. So what that means is you take your function, whatever it is, you replace x with our cos theta, you replace y with our sine theta, and then you multiply all of that by r, dr d theta. That r is extremely important. You cannot forget it, or you're going to get the integral wrong every time. So your dA here is not dr d theta, it's r dr d theta. And that's typical of a change of variables. You're going to have some term like that r there that you're multiplying everything by. But you have to remember the r, dr d theta. And that'll become ingrained in your memory after doing a few of these. So technically, it's a polar rectangle. So just like a normal rectangle, you can do either order of integration. So you could do d theta dr if you like. But usually dr d theta, usually not any more difficult. So I find it easiest just to remember the r dr d theta. But remember that r. Okay, so for example, let's integrate the function x plus y with respect to area over region D. So here D it's going to be the region in the first quadrant So the first quadrant, remember, is where both x and y are positive. Between the circles x squared plus y squared equals 4 and x squared plus y squared equals 16. So it's always nice to draw a picture. So x squared plus y squared equals 4 is the circle of radius 2 centered at the origin. And x squared plus y squared equals 16 is the circle of radius 4 centered at the origin. And we're just considering the region between those two circles, which lies in the first quadrant, where both x and y are positive. So that's our region D. Okay, so D is region bounded by circles. It's a piece of an annulus. It's a polar rectangle. So we're going to want to switch to polar coordinates to do this. So let's write D as a polar rectangle. So R is going to go from what to what? If we're looking at this set of points, they lie between distance what and what from the origin. So R goes from 2 to 4. Here's something which will come in handy later when we deal with somewhat more general regions. What I would do is I would draw a line a half line starting at the origin and look at where it intersects your figure. So the first place it intersects is the circle R equals 2. This will come in handy when we deal with more general polar regions. So it's always going to hit in this curve, R equals 2. And the furthest away we get, sort of the outer curve, all of those points lie on R equals 4. So R is going to go from 2 to 4. Theta is going to go from what to what? What is the smallest angle we make with the x-axis? 0. And what is the largest angle we make with the x-axis? Pi over 2, right? We go from theta equals 0 to theta equals pi over 2. Okay, so let's set up our integral. We have our bounds now. So R is going to go from 2 to 4. Theta goes from 0 to pi over 2. And now we need to rewrite our integral. So we were in rectangular coordinates involving x and y. We need to switch to polar. So wherever we see x, we replace with our cos theta. Wherever we see y, we replace with our sine theta. So x plus y becomes our cos theta plus our sine theta. And then what does dA become? Well, remember, burn it in your brain. dA is your r dr d theta when you switch to polar. So we're multiplying all that by r, and then it's dr d theta. So I'm just going to distribute that r through. So we get r squared cos theta plus r squared sine theta dr d theta. Right, I just multiplied everything by r. Does everyone see that? Okay, so now the integral is just going to work like it normally does. So we're doing the inner integral. So we're integrating with respect to r. So we're treating theta as a constant, right? So r squared cos theta, integrating with respect to r, treating theta as a constant. R squared becomes 1/3 r cubed. Cos theta hangs around as a constant multiple. So we get one-third r cubed cos theta, and then same thing, r squared sine theta becomes 1/3 r cubed sine theta. And we're evaluating that from r equals 2 to 4. So we get 64 over 3 minus 4 over 3. No. Yes, yes. Minus 8 over 3. Sorry, 64 minus 8. So we get 56 over 3. Plus 56 over 3 sine theta. So that's our inner integral. So we integrate theta from 0 to pi over 2. 56 over 3 cos theta plus 56 over 3 sine theta d theta. And we can just pull, let's just pull the 56 over 3 out. So cos theta becomes sine theta when we integrate, and sine theta becomes minus cos theta. And we're evaluating that from theta equals 0 to pi over 2. Okay, so sine of pi over 2 is 1, cos of pi over 2 is 0, minus sine of 0 is 0, minus cos of 0 is 1. So we get 56 over 3 times 1 minus negative 1. So we get 112 over 3. But once again, the important thing is setting up, understanding how to set up the integral. After you set up the integral, then it's just normal straight evaluation. There's nothing special about it. But any questions about setting up the integral? Okay, really quickly, let's look at more general polar regions. So, unlike with general regions in X and Y when we're dealing with rectangular coordinates, really for the general polar regions, we're only letting R be bounded by functions of theta. It makes life a lot simpler that way. So what this is going to look like is, so theta, well, okay, so R is going to lie between R equals R1 of theta and R2 of theta. And then theta is going to lie between numbers again, alpha and beta. So what that's going to look like oops. So this is our alpha. That's our beta. So R is going to lie between sort of two curves here. So this inner guy is going to be R equals R1 of theta. And this outer guy is going to be R equals R2 of theta. And this is going to be a more general polar region. So if this is your D, R goes from R1 of theta to R2 of theta, theta goes from alpha to beta. You will probably not be surprised to learn we do the exact same thing as we did before, but now you have to integrate with respect to the variable bounded by functions first. So x becomes r cos theta, y becomes r sine theta, dA, like we said, becomes r dr d theta. And we have to do the r first. The inner integral has to be with respect to r, because you have to integrate with respect to the variable bounded by functions first. And then theta goes from alpha to beta. So exactly the same as in rectangular coordinates, except you need to do the coordinate change. Okay, so really quickly, let's look at a region and describe it in this way. So let's evaluate, except we're not actually going to evaluate because we won't have time. But let's set it up. The integral over d of 1 over square root x squared plus y squared with respect to area. And here d is going to be the region. outside x squared plus y squared equals 1, and inside the region x squared plus y squared equals 2x. I'm going to go through this really quickly. If you need to go, feel free. But I want to get through this example really, really quickly. Okay, so we all know what x squared plus y squared equals 1 is. That's a circle centered at the origin of radius 1. But how about this x squared plus y squared equals 2x guy? Well, the way it's written, it's not super recognizable. But if we rearrange that, if we bring this 2x over, we can complete the square, right? So we complete the square by adding 1 here and adding 1 here. So we get x minus 1 squared plus y squared equals 1. And so we recognize this as a circle of radius 1 centered at 1, 0. So it's often good to sketch these regions. So we want the region inside that circle centered at 1, 0, and outside the circle centered at the origin. So we want this region here, this little crescent moon looking thing. Okay, so the way we're going to figure out the bounds for r and for theta is we're going to draw a straight line starting at the origin through our region D. Okay, so when we do that, so the closest we get to the origin is we're going to hit points on this circle, this inner circle, right? So that's the circle of radius 1 centered at the origin. What's the equation of the circle of radius 1 in polar? All of those points have in common. So all of those points are r theta. They have in common r equals 1. So that's our inner bound for r equals 1. Our outer bound for r is, well, we hit this circle centered at 1, 0. And so this one, we're going to have to figure out the equation. It's going to be r equals some function of theta. We're going to have to figure that out. So there's a reason we wrote it in this form. And that's because it makes it much easier to put in polar. All right, so x squared plus y squared. You should remember this. We said earlier, x squared plus y squared is equal to r squared. So the left-hand side here, when we convert to polar, becomes r squared. 2x is 2 times r cos theta in polar. We want to get this as r equals something, so we can just divide both sides by r. So we get r equals 2 cos theta is the equation of this guy here. So this guy here is r equals 1. And the furthest away we get was this circle, which we said is r equals 2 cos theta. So those are bounds for r. So the bounds for theta are going to work as follows. So theta is going to go, from this angle here to this angle here. Right, so we're going to use a negative angle. For that one, and a positive angle for this one. Notice this, it goes out to the point where the two meet down here and where the two meet up there. So we're going to look for the meeting point of the two circles and figure out what the theta is for those guys. So we're going to look at the intersection of the circles to find out what theta is. Well, the circles are r equals 1 and r equals 2 cos theta, right? To find the intersection of the two, well, they're both r equals something, so we set them equal to each other. 1 equals 2 cos theta. Cos theta equals 1/2. So cos theta equals 1/2, where x is negative. What is our theta? It's going to be negative. So let's look at the upper one. So this guy up here, our upper bound, theta equals 1/2. Up here, what is this angle? Pi over 3. And then for the lower guy, we're going to get negative pi over 3. And so that's why drawing a picture is important here. So I hope this isn't confusing. So you need to be careful. So you might be tempted to say, okay, just use positive values. So here we have pi over 3. And here, then this guy is going to be, say, 2 pi minus pi over 3. So let's say 5 pi over 3. But if you did pi over 3 to 5 pi over 3, that would not work because that would be this region here. And we're not in that region, we're in this region in here. So we're using negative pi over 3 to pi over 3 because we want the region in here. So make sure all your points that you're considering are going to be in an interval, like a contiguous interval there. Does that bit make sense? That's maybe the most confusing part of this one. Okay, so we have our bounds for r, we have our bounds for theta. And I've gone on way longer than I wanted to, but let's convert our integral. Okay, so r is bounded by functions. We need to do that first. R goes from 1 to 2 cos theta. Theta goes from negative pi over 3 to pi over 3. Okay. X squared plus y squared. What is 1 over square root x squared plus y squared when we change this to polar? So x squared plus y squared becomes r squared. 1 over the square root of r squared is 1 over r. And then dA becomes r dr d theta. And so we just get the integral from negative pi over 3 to pi over 3 and r goes from 1 to 2 cos theta of dr d theta. 1 over r and r cancel. And that's our integral. And if you want, you can evaluate that yourself, but that's our integral. Okay, my apologies. That went over a lot longer than I wanted. But any questions about any of this?
Could you mind going over again just quickly, getting the angles? I kind of didn't understand that the first time.
Getting the what? Angles?
The angles like negative pi over 3 and pi over 3.
Okay, so that's kind of the hardest part. So, I mean, it's kind of a busy figure here. But notice, so the biggest angle of any of the points in this region is going to happen at this upper intersection here.
Mm-hmm.
And the lowest angle we're going to get is going to happen at this other intersection here. So we're going to want to have a continuous, so we want a continuous interval of angles, which describes everything in here. So since we start out below the x-axis and go above the x-axis, what I'm going to want to do is I'm going to want to start out with a negative angle and then go up to a positive angle, just so I have a continuous interval of angles describing all my points on here. If you really wanted, if you hate negative angles, you could say, okay, this is, when we figure it out, okay, this is 5 pi over 3, and that goes up to like 7 pi over 3 or something like that. But that's maybe even more confusing. But does that point make sense?
Yeah, that makes sense.
Okay. So the way we're going to do that is we know those angles happen at the intersection of the two circles. So we write the equations of those in polar coordinates. The first circle is r equals 1, and the second is r equals 2 cos theta. And so we want to find the angle theta of intersection. Well, we know it's r equals something, so the right-hand side's equal to each other. So we get 1 equals 2 cos theta. So we know at the points of intersection, cos theta is equal to 1/2. And so we need to find the lower bound for theta where that happens and the upper bound for theta where that happens. So normally if I tell you cos theta equals 1/2, you would say, okay, theta is equal to pi over 3. But that corresponds to this angle up here. And of course, that's not the only angle for which theta equals cos of theta equals 1/2. The same is also true for cos of negative pi over 3, which is this guy down here. Not big.
So what you did was from the first equation, like finding where R lies. So we took that equation for what we know, like those bounds, like R equals 1 and then R equals 2 cos theta, set
Right,
those
so
equal
we're
to each
writing the
other and then solve for cos.
Yeah, we're writing the equations of the two circles in polar. And then
Mhm.
usually finding theta is going to be easier from those equations.
Okay.
Yeah. So we have the two equations. You're looking for the intersection, and you're setting them equal to each other, basically.
All
One
right.
equals
Sounds
2
good.
cos theta. And that's true for theta equals negative pi over 3 and pi over 3. And then we're looking at everything between those.
Okay. Thank you.
All right. Later.
All right. Have a great weekend.
You too.